Guys, in this video we're going to be looking at empirical and molecular formulas. By the end of this, you should be able to calculate the empirical and molecular formulas of compound from percent composition and molecular weight and do combustion analysis problems. So when we think about an empirical formula, it is the compound's smallest whole number ratio of atoms. So empirical formula. Smallest whole number ratio of atoms in a compound. And then the molecular formula is going to be some multiple of that empirical formula. So just as a kind of reminder from previous unit as we've already gone over this. So the way that we do this, so we've gone and determined percent composition earlier, but now we're going to take that percent composition and solve for our empirical formula. And we do this by assuming a 100 gram sample. So if you assume a 100 gram sample, then the percent mass becomes just that gram amount. So if you have 50% of carbon, it becomes 50 grams of carbon. That makes it a lot easier to work with. So you assume 100 grams, you multiply by the percent, and that takes you exactly from percent to grams. And then once you have your grams of each element, you're going to use their molar masses to go from grams of the element into moles of each element. And then using your mole ratio, you can determine your empirical formula. And of course, I find this easiest just with an example, so let's try one. We've got ascorbic acid. It contains 40.92% carbon, 4.58% hydrogen, and 54.5% oxygen by mass. We want to know what the empirical formula is. So if we have 40.92% carbon, assume 100 grams, we have 40.92 grams of carbon. We're going to do the same thing for oxygen and hydrogen. So we have 4.58 grams of hydrogen and 54.50 grams of oxygen. So just assuming that they're all at 100 grams. It doesn't matter. The percentage is intrinsic, so it doesn't matter the amount. We can assume any amount. Once we have our grams, we're going to convert each of them into moles using the molar mass from the periodic table. So carbon is 12.011 grams per 1 mole. And when we divide that out, we get 3.407 moles of carbon. We're going to do the same thing for hydrogen and oxygen. So 1 mole of hydrogen, and this is atomic hydrogen. So 1 hydrogen, 1.008 grams. And we get 4.54 moles of hydrogen. And then 1 mole of oxygen. Again, atomic oxygen. So it has a mass of 15.999 grams. Gives us 3.406 moles of oxygen. Now we're going to take our smallest one and divide all the rest of them by it. So our smallest is oxygen, so we're going to divide all of them by 3.406, 3.406, and 3.406. This gives us 1, and then we take 4.54 divided by 3.406. We get 1.33. Now, we know our empirical formula has to be whole number ratios. So we have to think at this point, how do we get to a whole number ratio here? We can't just say, oh, that's close enough to 1, because it's really not. This is 1 1/3. So if we take all of these, multiply, and whatever you do to 1, you have to do to all of them. If we multiply all of them by 3, we get 3, 4, 3. So this is going to be an empirical formula of C3H4 So that is our empirical formula of ascorbic acid. Okay? Now, oftentimes we want to figure out what our molar mass is or our molecular formula is. So a lot of times we want to figure out what our molecular formula is, and we can do this very easily by remembering that our empirical formula, we multiply it by some number to get to our molecular formula. So our molecular formula is some multiple of our empirical formula. So all we need to do, if we are dealing with AMU, we're going to take our molecular weight, divide it by our empirical formula, weight, and this is going to give us a whole number multiple. And this we will multiply our empirical formula by. So all the numbers within our empirical formula. If we are dealing with grams per mole, it's basically the same thing. Instead, we're taking molar mass, dividing that by our empirical formula, molar mass. And that again will give us a whole number multiple, which we will then multiply by our empirical formula. So let's try that out. So we've got ascorbic acid, C3H4O3, has a molecular weight of 176.12 grams per mole, and we want to know what its molecular formula is. So this is our molar mass of our full compound. This is the molar mass. This is our empirical formula that we need to find the molar mass for. So we take 3 times by 12.011 grams per mole. Giving us 36.033 grams per mole. Then we have our hydrogen. There's 4 hydrogens. Multiply it by 1.008 grams per mole. Giving us 4.032 grams per mole. And then our 3 times by 15.999 grams per mole. Giving us 47.997 grams per mole. Add that all together. And we get 88.062 grams per mole. So we're going to take that 176.12 gram per mole divided by 88.062 grams per mole, and we get a value of 2. So we're going to take our ascorbic acid's empirical formula, multiply it by 2. So C3H4O3 times by 2 gives us our molecular formula of C6H8O6. Wonderful. Another way we can determine our empirical formula, besides just taking percentages, is what's called combustion analysis. Combustion analysis, however, only works with a hydrocarbon. So we take a hydrocarbon sample, we flow oxygen gas over it, and we produce carbon dioxide and water. That carbon dioxide and water is then absorbed onto a surface, and the mass before and after the reaction can be taken to figure out how much you have. So some things in combustion analysis, you have to have a hydrocarbon. It can be a hydrocarbon with a heteroatom, that's fine. You have to know the initial mass of your sample. So whatever your hydrocarbon mass is, you have to have that in order to solve for this. And then you're going to also know masses of water and carbon dioxide after combustion. So this is taking some hydrocarbon, and again, it could be could contain a heteroatom, that's fine, reacting with oxygen gas to produce some amount of carbon dioxide and some amount of water. From this information, you're basically going to go from grams of hydrocarbon. From this information, you're basically going to go from grams of carbon dioxide and grams of water into moles of carbon dioxide, moles of water, and then from there, you can get to moles of carbon and moles of hydrogen. And here is how you can find your empirical formula. Let's look at the flow chart on how to do this. So you start out with mass of carbon dioxide and water produced. Using the molar masses of carbon dioxide and water respectively, you can get into moles of carbon dioxide and moles of water. Using the fact that there is one carbon atom per molecule of carbon dioxide, you can convert from moles of carbon dioxide into moles of carbon. And then using the molar mass of carbon, you can get to mass of carbon. Getting to this last point over here is only important if we have a heteroatom, and I'll talk about why in just a minute. Same thing with water. However, water has 2 atoms of hydrogen per molecule of water, so that needs to be taken into account when going from moles of water into moles of hydrogen. And then I guess we can go into grams of hydrogen using the molar mass. And again, this is if we have a heteroatom that this becomes important. Okay, so let's try it out. We've got the combustion of 25.00 grams of ethylene glycol, and this produces 3.545 grams of carbon dioxide and 2.177 grams of water. We want to know what our empirical formula of ethylene glycol is. So pretty easy. We're going to take our grams of our products, so our carbon dioxide and our water, and from there we're going to be able to get to our carbon and oxygen. Now, notice this is called glycol. It has an ol, and when we talked about this, remember this is a oxygen-containing species. So we're going to have to do an additional step to figure out our oxygen beyond this flowchart, but we are going to have to use this portion of the flowchart. Okay, so let's look. We're going to go from our grams of carbon dioxide into moles of carbon dioxide using our molar mass, 44.0 grams per 1 mole of carbon dioxide. So when we take our 3.545 divided by 44, we get 0.0806 moles of carbon dioxide. And then for every 1 mole of carbon dioxide, we have 1 mole of carbon, giving us 0.0806 moles of carbon. And then we want to convert that into grams of carbon using the molar mass of carbon, 12.011 grams per 1 mole of carbon. Multiplying that out, we get 0.968 grams of carbon. Do the same thing for our water. So 1 mole of water has a mass of 18.0 grams. So we take our 2.177 divided by 18.0, and we get 0.121 moles of water. And now for every 1 mole of water, we have 2 moles of hydrogen. So multiply this by 2, and we get 0.242 moles of hydrogen. And then we want to convert that into grams of hydrogen using our molar mass of atomic hydrogen. And we get 0.2 0.244 grams of hydrogen. Okay, the last thing we need to do is we need to figure out our amount of oxygen, because we have already shown that this is an oxygen-containing species. We do this by taking those grams we just got and subtracting it from our sample. Our sample contains carbon, hydrogen, oxygen. We know from our conservation of mass that the number of grams of hydrogen will be the same on both sides, the number of grams of oxygen will be the same on both sides, and the grams of hydrogen will be the same on both sides. We already know our grams of carbon and hydrogen. If we subtract it from our initial sample amount, the thing that's left over is our grams of oxygen. So we'll take that 2.500 grams of our sample, subtract 0.968 grams of carbon, and 0.244 grams of hydrogen, and this gives us our grams of oxygen at 1.288 grams of oxygen, and then we're going to convert that into moles of oxygen. Again, this is atomic, so 15.999 grams per 1 mole. Giving us 0.0805 moles of atomic oxygen. And now we're going to divide by our smallest amount. So dividing by 0.0805. This gives us 1. This gives us 1. And this gives us 3. So we have CH3O as our empirical formula. Okay, that is it. Talk to you guys in the next one.